Greetings to all viewers. This is Professor Ankit Singh. We'll now move to the next topic, that is horizontal transition curves. Let us try to understand what a transition curve is. A transition curve is provided to change the horizontal alignment from straight to circular curve gradually and has a radius which decreases from infinity at the straight end, that is the tangent point, to the desired radius of the circular curve at the other end, or the curve point. Okay, so transition curve is a curve which has varying radius at each point and which is used in order to connect a straight to a circular curve. Okay, so this is nothing but it is used to smoothen the path. Okay, so a circular curve will have a radius r throughout the curve, and a straight road would have a radius infinity. Okay, so we provide a transition curve which joins the circular curve to the straight. This transition curve will have varying radius, okay, at all the points. Okay, so it will have a radius of infinity at the point of start or the tangent point, and it will have a radius of r at the point at which it connects the circular curve. Okay, and similarly when it leaves the circular curve, it will start with a radius of r and it will end with a radius of infinity when it joins the straight path. Okay, so this is a transition curve. Now let us see what are the objectives of providing transition curves, or why do we need transition curves. First point, to introduce gradually the centrifugal force between the tangent point and the beginning of the circular curve, avoiding sudden jerk on the vehicle. This increases the comfort of passengers. Okay, so as we all know and we have studied earlier that we, or the vehicle or the driver that is traveling on a horizontal curve, experiences a centrifugal force, okay, towards the outer end of the curve. Now if there is no transition curve provided in between the straight and the curved or the circular curve, then there would be a sudden centrifugal force experienced by the driver at the start of the circular curve. Okay, so we don't want that sudden jerk. In order to reduce that sudden jerk, what we do is we provide a transition curve. Now what is the advantage of providing a transition curve? Since the radius increases or reduces slowly, hence the centrifugal force will also be induced gradually. Okay, so this is the advantage, and since the gradual increase in centrifugal force happens, hence there would be better comfort provided to the passengers since there is no sudden jerk. Okay, so second point, to enable the driver to turn the steering gradually for his own comfort and security. Okay, so since the curve is being induced gradually, the steering can also be done gradually. Okay, this also increases comfort and security. To provide gradual introduction of super elevation. Okay, as we all know, in order to counteract the centrifugal force at the circular curves, what we do is we raise the outer portion of the road with respect to the inner portion, that is known as super elevation. Now if we join the straight road to the circular curve without providing any transition curve, then at the point C we would need to provide a sudden super elevation. Okay, so that is not feasible. Hence what we do is we provide a transition curve, and with help of the transition curve we slowly provide the super elevation. We increase it from point B gradually to point C, and at point C there is fully attained super elevation. From point C to point D there would be full super elevation as per design, and later on again from point D to point E it will again reduce. Okay, so the transition curves help us in providing super elevation. to provide gradual introduction of extra widening. Okay, same as super elevation is provided gradually from point B to point C, here also extra widening would be provided from point B to point C gradually. The width of the road would be increased from point B to point C, then again it would be constant from point C to point D, then again it would reduce from point D to point E to enhance the aesthetic appearance of the road. Okay, so it also helps in enhancing the aesthetics of the road. It would be better if we can see a increase in width, a gradual increase in width as compared to a sudden increase in width. Okay, so these are the objectives of providing the transition curves. Now there are types of transition curves. There are mainly three types of transition curves. Okay, the first one is spiral, the second is lemniscate, and the third one is cubic parabola. Okay, different types of transition curves are spiral or clathoid. Spiral is also known as clathoid, or cubic parabola, and lemniscate. IRC recommends spiral as the transition curve because, okay, so IRC recommends that we use this spiral as the ideal transition curve. Okay, why is it? There are a few points, we'll discuss them. It fulfills the requirement of an ideal transition curve, that is, rate of change or centrifugal acceleration is consistent. Okay, so here you can see in this curve, the spiral, as the length increases the radius would decrease. Okay, so there would be a gradual transition. Second, radius of transition curve is infinity at the straight edge and changes to r at the curve point. Okay, so here the radius would be maximum, and as the length increases it would be less. So this, it would go on to get lesser and lesser. Okay, with increase in length the radius would reduce. So ls is directly or inversely proportional to radius of the curve. So what does this mean? Ls is nothing but length of transition curve. It is inversely proportional to radius of the curve. Means as the length of the transition curve would increase, the radius of the curve would reduce or decrease. And the calculation and field implementation is very easy. Hence, spiral is used as an ideal transition curve. Now, when we design, we need to find out the length of the transition curves. There are three methods or three sets of formulae that we use in order to find the length of transition curves. The length of transition curve should be determined as the maximum of the three criteria. Okay, we use three criteria, and out of these three criteria, whichever criteria would provide us with the maximum length, we will adopt that length. Okay, so the first criteria is rate of change of centrifugal acceleration. Second is rate of change of super elevation, and third is empirical formula given by IRC. Now let us have a look at those formulas first. Okay, so length of transition curve. Firstly, the formulas would differ for plain and rolling terrain and hilly and sloping terrain. Okay, hilly or mountainous terrain and sloping. So, and under the plain terrain there would be three criteria. First is rate of centrifugal acceleration. Second is rate of attainment of super elevation, and third is empirical formulas as per IRC. Okay, so now first let us look at the formula for plain terrain conditions. Okay, so the first condition was rate of change of centrifugal acceleration. Here the formula is given as C is equal to 80 divided by 75 plus V. Okay, what is this C? Firstly we need to find out the C value. Okay, so C is nothing but it is the rate of change of centrifugal acceleration. Okay, so after we find out the value of C, we can find out the formula, the value of transition curve length, that is L1 is equal to 0.0214 V cube by RC. Okay, here C is nothing but rate of centrifugal acceleration that we found out, V is velocity in kmph, okay, and R is radius of curve in meters. Okay, so this is the first criteria. The second criteria is rate of change of super elevation. So these are those formulas for rate of change of super elevation. Again, in this there are two criteria. Super elevation at the outer edge, it is raising of the road with the at the outer edge with respect to inner edge, then the formula is different, and raising of the outer edge with respect to the center line, then the formula is different. Okay, so we can attain super elevation by either raising the outer edge of the road with respect to the inner edge, or what we can do is we can raise the outer edge with respect to the center and we can lower the inner edge with respect to the center. So there are two conditions of attaining that super elevation. So in the first condition, that is raising outer edge with respect to inner edge, the formula is L3 is equal to W plus WE into NE. Okay, here W plus WE is nothing but W is the width of the road in meters, WE is extra widening, okay, and NE is the slope provided. Okay, so this slope value would be given in the question. The rate of change of this raise for 0 to E achieved gradually with a gradient of 1 in n over the length of transition curve. Okay, so this n 1 in n value would be given in the question. If not given, then we need to adopt some standard values, and the typical range will vary from 60 to 150. So the n value will vary from 60 to 150. Okay, then using this formula we can find out the length of transition curve. Now when the super elevation is achieved by raising the outer edge with respect to the center line, okay, then the formula is this: L3 is equal to W plus WE divided by 2 into NE. Okay, the only difference here is when we raise with respect to the center line, it will be divided by 2. Okay, since the inner part we are lowering it and the outer part we are raising it above, and in the first case there is no lowering, there is only raising. Okay, and the third criteria is the empirical formula given by IRC, that is this: for plain terrain the formula is given as L2 is equal to 2.7 V square by R, where V is velocity in kmph and R is radius in meters. Now we'll find out L1, L2 and L3 for if the condition is for plain terrain. Okay, now whichever is the highest value among L1, L2 and L3, that value would be adopted. Okay, that is the design length of transition curve. Now the same set of formulas are also used if the terrain given is hilly. The only difference is in the empirical formula. Okay, in the empirical formula for hilly and mountainous terrain, the formula is L2 is equal to V square by R. It is not 2.7 V square by R, but it is only V square by R. Okay, so understand the difference. And in this case also we would find out L1, L2 and L3, and the maximum of these three values would be adopted as the design transition curve length. Okay, so we'll now move to the next topic, that is curve resistance. When the vehicle negotiates a horizontal curve, the direction of rotation of the front and the rear wheels are different. Okay, we already know this. I've explained this during explaining the extra widening part. Okay, that the paths would be different and the rotation also would be different from for the front wheels or front axle and the rear wheels or the rear axle. The front wheels are turned to move the vehicle along the curve, whereas the rear wheels seldom turn. Okay, they rarely turn. This is illustrated in the figure. Here in this figure you can see. Okay, this is the front axle and this is the rear axle. Now, the rear wheels exert a tractive force capital T in the PQ direction. Okay, in the PQ direction. Okay, the rear wheels are exerting a tractive force or torque. Okay, this torque is required in order for the vehicle to move forward. Now that value is T. The tractive force available on the front wheels is T cos alpha. Okay, or here it is given as A, this can be alpha. Okay, so this is nothing but the angle. Okay, angle of steering. Okay, it is the deflection angle, this. So if along PQ the torque value is T, then along PS it would be T cos A or T cos alpha. Okay, we know resolution of forces. Okay, so this is T cos A or T cos alpha. Okay, the tractive force available on the front wheels is T cos alpha in the PS direction as shown in the figure. This is less than the actual tractive force T applied. Okay, so we know that cos of 0 is 1. Okay, and as the angle increases the value would reduce. Okay, so we know cos 90 is 0 and cos 0 is 1. So now this alpha or A value would be in between 0 and 90, so which is obviously less than 1. Okay, so when you multiply with that with T, then the T cos A or T cos alpha would be less than capital T. Okay, this is understood. Hence, the loss of tractive force for a vehicle to negotiate a horizontal curve is given as curve resistance CR is equal to torque in the straight direction capital T minus torque while steering minus T cos alpha. Okay, so this is nothing but the curve resistance offered during any turning operation on a horizontal curve. Okay, so we'll next move to vertical alignment. I'll start with this topic in my next lecture. Thank you.